Hello, today we're continuing with our GCSE physics revision series and we're looking at seismic waves and infrasound. For our purposes, the Earth is made up of, as it were, four distinctive layers. On the outside we have a relatively thin, rocky crust. Then underneath the rocky crust there's a layer which is called the mantle. It's basically hot rock, sometimes it's molten rock, and where it's molten, that means to say it's almost liquid form, that is called magma. And when that magma bursts through the surface, as it does from place to place, where the magma bursts through the surface, that is a volcano, and you get that molten rock pouring out of the volcano. Then there is a core and an outer core. So this is the mantle, this is the outer core, which is very hot, liquid rock, mainly iron but other rock. And in the centre you've got the inner core, which is actually solid, mainly iron. Let me move that up. How can it be solid right at the middle? Well, it's under intense pressure. There are two ways that you can create solids. One is what you might think is the normal way, cool things down. The other is to keep things hot, but increase the pressure, and increasing the pressure will create a solid out of liquid. So right at the heart of the Earth, there is a very hot but solid iron core, surrounded by an outer core which is liquid iron, very, very hot iron and rock. And then you've got hot rocks, mainly solid but sometimes liquid, in the mantle. Where it is liquid or molten, it is called magma. And then finally a thin Earth's crust. And sometimes the magma bursts through the crust, and when it does, that is called a volcano. Now the surface or crust of the Earth is made up of what are called tectonic plates. That is to say, they're sections of the surface of the Earth. And underneath them, remember, is the mantle, which consists of some molten magma. And what these tectonic plates are doing is they are moving as the magma underneath the surface, the molten rocks, as that moves, and as the currents in that move, so the tectonic plates are themselves moved. Of course, minuscule speed, but they are moved, and sometimes the tectonic plates will crash into one another and they'll be forced upwards, and that's how you get a lot of mountain ranges. Indeed, that's how the Himalayas are thought to have formed. But of course you also get friction. As the magma moves underneath the tectonic plate, the plate itself may not move. I mean, think for example of a very heavy box on the floor. You come along and you push it, it may not move because friction is stopping it. So you push it a bit harder and still friction stops it. And then you push it a bit harder and all of a sudden it moves. And it doesn't move gently, it tends to jerk forward. And the same thing happens here. The magma is moving under the surface, but friction is stopping the tectonic plate from moving, and then all of a sudden the forces are so great that they overcome the friction, and there's a sudden movement of the tectonic plate, and that is an earthquake. When an earthquake occurs, it causes a shock wave. We call it a seismic wave. These are measured on a piece of equipment called a seismometer, and the graphical output, which shows the extent of the shock wave, is called a seismograph. There are three types of seismic waves, P, S and L. You won't need to know very much about the L wave. First, the P waves. The P waves are longitudinal waves, so in that sense they're rather like sound. They vibrate, as it were, backwards and forwards in the direction of motion. They can travel through solids and liquids, so the key point here is they are able to travel through the liquid outer core of the Earth, as well, of course, as going through all the solid parts of the Earth, they refract as they go through different densities. So as the density of the Earth increases as you go further in, so the waves refract, but particularly when they come to a boundary. So for example, when they come to the boundary between the solid mantle and the liquid outer core, they refract extensively, and they travel faster than S waves. So you can measure the difference in time between the arrival of the P wave and the subsequent arrival of the S wave. S waves, on the other hand, are transverse. They're rather like light waves, but they only travel through solids. So critically, they cannot travel through the liquid outer core. And as I've already said, they travel slower than P waves. L waves are a combination of transverse and longitudinal. They travel through both solids and liquids, so all parts of the Earth, but they are very, very slow. But the key point for all of these waves is that the more dense the material is through which they are passing, the faster they travel. And that leads, of course, to the process of refraction. As you go into more dense material, you go faster. So, here is the Earth. That's its thin outer crust. Here is the inner core. Here is the outer core. And here, of course, is the mantle. So we've got crust, mantle, outer core, inner core. And we're going to first look at P waves. P waves travel, remember, through both solids and liquids. And let's suppose that the earthquake happens here. Well, we're going to get a P wave which will travel in all directions through the Earth, but as it travels through the Earth, it is constantly being refracted because of the change of density. So instead of travelling in straight lines, it travels in curved lines, and it can be detected. So far, so good. It's just gradual curves of the line reflecting the fact that the densities are changing. But when it gets to the outer core, which is liquid, there will be a significant refraction. And then when it gets to that surface here, between, again, the outer core and the mantle, there'll be another refraction, like this. So you'll notice that the P waves will be anywhere from here to this point here. You can detect P waves. But you won't get a P wave in this section here, because the P wave that would get there has been refracted away. This is the next point at which you can pick up P waves. P waves, of course, will travel straight through the Earth, straight through the core and out the other side. And of course there's a mirror image on this side, so there'll be another area like this, which is the equivalent of this, where you won't get P waves on this side of the Earth. But everywhere else, you'll get P waves. So no P waves in that little section, because they were just gradually refracted up to this point, but then they get significantly refracted through the liquid core, and that means that there's a stretch of the Earth where you don't get P waves. So if you can work out where there are no P waves, that gives you a hint as to where the earthquake was. And if you can identify all around the world, there's not just 2 points, but of course this is a three-dimensional object, so there will be, as it were, a region around the Earth where you won't pick up P waves, and that will enable you to identify precisely where on the Earth the earthquake has happened. What about S waves? Well, they only travel through solids, so they can travel through the mantle, but they're travelling slower than the P wave. But once they get to here, that's all they can do. And let's just do the other side so we can show you what's happening there. As soon as they would attempt to go through this liquid outer core, they can't, because S waves don't travel through liquids. Consequently, you can't get an S wave in any of this region here. S waves only can occur in these regions because they cannot go through the liquid outer core. So you'll notice that there's a huge chunk of the Earth where you can't get an S wave, and that there is a band on the Earth where you get neither an S wave nor a P wave. And let's just remind ourselves, the reason that the waves are bending is because they're constantly going through increasing density as they go through the Earth. So that means there's a gradual ongoing diffraction the whole time. But when they come to the boundary between the mantle and the outer core, that's solid to liquid, there is a significant diffraction, and that's what causes this P wave diffract in this way. The S wave cannot go through liquids, so it is constrained only to go through these areas because anything else would require it to go through the outer liquid core. Where an earthquake happens under the sea, if that's the surface of the sea, and you've got an earthquake happening under here, that can lead to the production of a very high wave. That's called a tsunami. And that tsunami can travel over hundreds of miles and be very high. So when it eventually hits land, it can cause devastation on that land. How can you measure the distance from any particular point on Earth to the epicenter, which means the middle of where the earthquake took place? Well, you need to find a place where you can receive both P and S waves. Remember, the S waves won't go through the liquid core, so there's only a limited region around the Earth where they will appear. And then you measure essentially the time difference, which I'll call delta T, between when the P wave arrives and when the S wave arrives. So what is the time between those two? And knowing the speeds of those waves through the Earth, you can deduce where the earthquake actually took place on Earth. The problem is that just at present there is no way of predicting when an earthquake will take place. We don't have the means to identify when a tectonic plate is, as it were, about to unleash its fury. All we can do is to identify where earthquakes have taken place before and assign some kind of probability. If you've already had an earthquake, then possibly you'll get another one. If you've been in an area where there haven't been any earthquakes, then you probably won't get one, but you can never be absolutely certain. In an earlier video, we talked about ultrasound, that is sound whose frequency is too high for the human ear to hear. That's generally at least more than 20 kilohertz. There's another form of sound called infrasound, which is too low for the human ear to hear. It's generally less than 20 hertz, 20 cycles per second, and this is associated with volcanoes, avalanches, ocean waves, hurricanes, and earthquakes. They all produce this very, very low sound, infrasound, which can travel hundreds of kilometers through the Earth and is one of the main means by which we can detect volcanic activity by detecting infrasound waves which may have come from a volcanic eruption.